Hello, good evening everybody. So, we were talking about the different types of ceramic materials, and one of the type we are discussing is the second category, basically the specialty ceramic materials. So, this is of the special quality. So, it can have also two different types, one is the coarse type and another is the fine type. And within this coarse variety, we have again subdivided into two, like that porous and the non-porous part. And non-porous part, which is the porous material, also we get that fusion cast bricks. So, the brick material, if we consider that sometime some special purposes, we can use this sort of brick material also, which are coming under this category of specialty ceramic materials. And what about the porous type? The porous type can have some of these as the alumina rich rock type, then silicate rock type, that we can also know, and the basic refractory products are also under this category, and the clay bonded silicon carbide. So, if we have some amount of clay in it, and also the silicon carbide material can also be of this type. Then going to the other side, that means the fine variety. So, fine variety can have also two types, the porous type and the non-porous type. And under porous type, it has different types of pores of different sizes. It can be used as the insulation material or the filter material. If we consider that you can have a particular type of pore size, so that can be very much useful for a filtering material. The way we use the sintered bed crucibles, the way we use the filter papers, we know that the different types of pore sizes are important. Even if we know that the different types of filter papers what we use, the different types of filter paper can also give us the corresponding filtration efficiency regarding the particle size what are there in a precipitate or some other material which we are trying to filter out. So, for the non-porous, which is a little bit of other type where the porous thing is not there, we simply use some of them as the typical oxide ceramics. The name will also tell you that we will also find out that what are those oxide ceramics. That means they are basically the metal ion based or sometimes the typical oxide material of some non-metallic part also. So, we can have the oxide ceramics and the non-oxide ceramics when no oxygen is present. That means other things are there, it can be carbide, it can be nitride. So, how we get these basically from the broader perspective, that how we get all these clay ceramic products. So, the thing is that you can have the clay and then we just process it for getting a good type of ceramic material starting from the different starting materials which are naturally available also. One of that material is the clay material, simply kaolin. When kaolin is there, we can mix it with quartz and we can mix with some amount of feldspar. So, the different composition of this material, so is basically a mixture. Then we go for the processing of this particular material to get the ultimate finished product as the new ceramic product. So, if we consider that what is that clay and that clay how we can use it. So, the kaolin mineral as a typical inorganic chemist, what we always try to understand that the typical chemical formula, always we try to know that what are the element wise composition for that particular material. So, it is nothing but it is aluminum silicate or aluminosilicate with certain amount of extra hydroxide groups. So, basically it is Al2OH4 Si2O5. So, the basic building block is your disilicate material, which is your Si2O5 material. So, the disilicate material is your building block, and on that basically we will be making all these ceramic products based on kaolinite or kaolin. Then another variety of clay we can have is the elytic clay, can have same type of composition, but is not the pure disilicate thing, it is basically aluminosilicate. So, aluminosilicate we all know very well that some of the silicon positions can be substituted by aluminium as Al3 plus. So, it can have a different property, it can have a different structure as well. So, when you get that, that means when you substitute this Si2O5 part by Si 4y minus y and ALY, that means some of these silicons can be substituted by simply your aluminum. So, the equivalent amount of silicon sites will be substituted by aluminum, and like that of your disilicate you can have again Al2OH whole 2 now, and also for charge balancing thing that it can have some extra amount of potassium as the potassium ion, or sometime simply the proton H plus which is solvated or having some water molecule attached to it. We know that H plus plus H2 giving you H3O plus. So, for charge balancing purpose is again very much related to that your Y value is defined. So, Y for aluminum, Y for number of silicon less than 4 minus Y, and the number of Y which is required for your charge balancing thing. So, the whole thing can be neutral considering that corresponding charge balance by the potassium ion or the simply proton. So, when proton is there, we know that that particular material can be very much acidic also. So, if we use this quartz material, why we are use this? The quartz is used basically as a lean clay, because this is basically a clay material and we are putting some amount of quartz in it, which is nothing but your SiO2 material. So, this SiO2 material, and is the purpose of this is that it reduces the shrinkage upon firing. So, when we fire it, the material will be fired. So, the shrinkage will be there, that means it is basically shrinking, that is the material which the voluminous one, and when it is going for the firing process, it basically going for the sintered bed formation or the shrinking thing. So, if the amount of quartz is more, the shrinking process or the amount of shrinkage will be less, and feldspar is basically acts as a flux material, because we know that some of these fusion basically sometime we can consider it as a fusion mixture. So, feldspar basically is some kind of fusion mixture and is also considered as a flux material during the fusion process. So, we can have all these three components, and these three components can be mixed to get a corresponding mixture, and when the mixture is processed in such a way that you get basically a finely ground material. So, the supply is that you have the finely ground raw material in your hand, and that basically after processing give you the fine ceramic products. So, the particle sizes are less, so you get a fine variety of that ceramic product if the grounding process of the raw material is well and the particle sizes are less. But if you have something different which is having a mixture of different particle sizes, because you cannot have very uniform particle sizes, then you get basically the quartz ceramic products, and that we also deliberately introduce the bigger particles which are non-uniform in nature, which are not of finer category, because we want to introduce the porosity within the material. So, it is basically giving you the quartz ceramic products. And then once you get the raw material in your hand, the next step will be the drying of this paste to flowing powders. So, you get the material, then you just dry it, because otherwise it can be a sticky material, and that material can be used for the drying purpose, and the drying purpose or the drying processes of that particular paste giving you a type of powder which is freely flowing. So, the free flowing powders we can have, and we basically, to get that free flowing powder, we basically use the spray drying. So, the material is being sprayed and in a hot chamber it is being drying. So, then the next process after drying is the forming process of getting this particular ceramic material. So, what is that particular forming process? The forming process is basically dependent upon some of the special qualities. It is dependent on the shape of the end product, what sort of product we are expecting. So, the forming process can vary also. Then always we can have some look for the required properties. We basically are looking for some amount of that particular type of property, and the size of the production run, that how much material we are using for a particular run, and particularly the volume or the size of that particular production run is also important for this particular forming process. Then after this forming process, we will just proceed for the casting process. We know that the casting, how we cast a particular type of material. So, it is also true for your ceramic material. So we can have a good particular type of mold or particular type of template in our hand, and the casting is being done of three different categories. The first one is basically is known as solid casting process, and in that solid casting process either it can be a plate like or sheet like thing, or it can be a three-dimensional one, and we basically, depending upon your mold or the template, we basically go for the casting process in a particular way that we put the material from the top. Then this variety, it can be a solid block, or sometimes we can go for this hollow block also. The hollow casting is there. If it is in a two-dimensional sheet, you get the middle portion as the hollow space. So the inner shape corresponds to the outer shape. So the type of inner shape what you can have. So on coating on all these positions, you can get this particular one as the hollow casting process. And the third category is your cored casting. Again, you can have a different shape of the inner mold, then inner shape corresponds to the core also, and based on that particular core, where you have this particular core, the circular thing, this is there, this is this particular sectional view of this particular casting, and the sectional view will tell you that you can have a cored casting process for them. Then we get for the corresponding plastic forming process. Then plastic forming process is nothing but is based on the plasticity of water containing clay ceramic paste. So what we can have the clay material, we finely grounded it, and the powder material is mixed with water, and then we can have mixing of that material giving you a paste. So the control of addition of water, how much amount of water we put, that will dictate or that will consider the quality of that paste. And based on that plasticity, because that particular paste can have a particular plasticity, and we can monitor or we can measure the plasticity of that particular paste also. In the form of the potter's wheel, as we know that the potters made that particular pots, the earthenware pots, the clay pots, what we know that it will be there, and the paste is basically the clay paste or the clay material mixed with water is poured on this. This is therefore the oldest known sort of forming process. So this particular one is a typical example like that of your potter's wheel. We know is a very old knowledge basically that can be utilized for that particular process, and which can be used for your forming process. And the material, since the material is present in a particular type of plasticity, that's why it is known as plastic forming process. Then other one can be a powder processing process. So powder pressing process is that when we can utilize for simple geometric form, that means the shapes are known with some geometrical object, geometrical variety you can have, and long production runs. So the run time for that production is long one, then we can use this powder pressing process, and is isostatic pressing process which can produce the molded articles with a very uniform density distribution. So this particular pressing process, which is isostatic, so this is basically a same static process, isostatic process, and this particular isostatic pressing process giving the molded articles which are utilized for the mold with a very uniform density distribution, because one part cannot be a very high dense one and another part is a low density one. So the uniform mixing is also very useful, and that uniform mixing is basically giving you a corresponding utilization for your powder pressing process. So these are the different forms of this forming process and the pressing process, which then can follow for the formation of the next step of the getting ceramic is your firing. So once we have this material, we have this molded one like that of your the potters make the different earthenware pots for us, and that is then introduced for the typical firing process. And in that particular firing process, what we get there is that your typical firing of the ceramics. So what we get there during that particular firing of clay ceramic products we can have, so is basically wet till, and the physiochemical processes can take place at that particular time. depending on some of the different types of these things, that means how we get this particular thing, that during the firing process the formation of mullite flakes and cristobalite. So, the crystals basically the mineralization form what we get basically during the firing process basically, because this evaporation is taking place, then high heat treatment basically changing the material from one form to the other. And the two typical mineral variety, we know that one is the mullite variety of flakes and another is the cristobalite. So, these two varieties can take place there while changing the typical character of that material or its physiochemical behavior or physiochemical property. Then as we have seen that basically the feldspar is basically the flux material. So, the melting of the feldspar can also take place, and during the molten feldspar it takes basically all the other material in it, and such that at very high temperature you get some uniform slurry material, and that slurry material is being then subjected for your firing process. Then at this time basically that other variety which is your quartz. So, the quartz can also go for your dissolution in this molten state. So, basically whatever we are handling, the way we mix in the chemistry laboratory the solid sample, then we put some solvent or other variety of in it, we basically mix it to get the solution. But when we do that particular reaction in the solid state, basically it is nothing but your typical solid state, high temperature solid state synthetic process. So, at high temperature when everything is in the molten condition, the managing of all these material, all these parameters will be sometimes very difficult. And also we know at what particular temperature feldspar is in the molten state, your silica and your quartz is also in the molten state. Then if we go for, that means that lowering of the temperature, that means something will come out definitely as in the solid form. So, the formation of the crystals in the mullite flakes, basically the formation of the mullite flakes, the first variety is then taking place as a typically needle shaped mullite material. The way we know that when a saturated solution is there and saturated solution at high temperature, if you allow to come it to the room temperature or if we cool down to a room temperature, the extra material which is not there, which is not allowing for their sufficient solubility of that particular temperature, we get back the excess solid amount as the small crystals. This is the basic fundamental theory behind it for the crystallization process. So, similarly with the temperature variation in the molten state also, whatever is generated out of this step is that your needle step mullite material. So, the reaction what is being taken out from there is that what we have seen that this particularly kaolinite or the kaolin material we have seen is the disilicate one, which is having the building block of your Si2O5, and that Si2O5 during that particular firing process we know that that has been converted to the metakaolinite. So, the metakaolinite is basically is a aluminosilicate structure having a particular type of aluminosilicate structure with the removal of some amount of water molecules over there. So, Al2O3 dot 2 SiO2 is the basic formula of that particular material, but it is a endless three-dimensional structure where the networking is there for SiO4 unit, the tetrahedral SiO4 unit and the aluminate unit, which are entangled for a three-dimensional structure which is similar to that of metakaolinite. Then this particular one through the formation, so the metakaolinite then at a other temperature, at other higher temperature, it can give you the alumina, the gamma variety of your alumina material. So, basically if we are taking that, so alumina as well as silica is getting separated out of that particular metakaolinite variety. Then the final thing, that means the step number 4 basically, and what we have seen that then the formation of mullite flakes as well as the cristobalite thing. So, the first part, so you can have that means Al2O3. So, the gamma form of this Al2O3 then is mixed, that means the further amount of SiO2. So, the stoichiometry is basically now changing, it is still 1:2, but 3 units of Al2O3 is being reacted with that of your 6 SiO2 unit, giving you two individual phases. One phase is for your mullite phase, which is your Al2O3 SiO2 with a 3:2 composition. Another is simply the cristobalite, which is typically a silica variety. So, these are basically in the solid state material, these all will be there, and we basically getting towards that particular ceramic formation out of this chemical reaction at high temperature. So, high temperature reactivity of these things, this ceramic material basically giving us some good material. So, material definitely can have very useful applications. So, if you now look at the application, once we get that from the starting material, the raw material we know, and how we handle those raw materials for getting these reactions and what are those chemical reactions at high temperature is taking place, that also we have seen. Now, if we simply categorize the properties and their applications, it will be therefore very much industrially important material, because to get all these things from the historically important fundamental knowledge of this making the different types of earthenwares from the potter's wheel is basically historically these are all important, but it has gave birth to a particular area of industry, which you know that there is a typical ceramic industry, and the engineering aspect of that ceramic industry will give birth of that of your ceramic engineering also. How we get the day by day, how we utilize all these things, whatever we have learned so far from the historical perspective is in our hand. So, what we try, the people will try definitely the new material, new application and new properties out of these, how you vary all these simple inorganic chemistry reactions. So, the inorganic reactions will definitely be applied at a very high temperature to get the different types of materials. So, one of them is your fine earthenware. What is that? Articles are porous in nature, they are white or ivory in color. So, that color thing is also very important and used in the manufacture of ceramic filters and diaphragms. Since you have a particular type of porous material that we have seen while we are categorizing all these things, that we have seen that it can be used as a filtering material like your filter paper or glass split material or the sintered bed material. So, it can be your ceramic filter or the typical diaphragm. Then we know that the kitchenwares or the household utensil also we can have from out of these earthenwares, and the sanitary wares are also very much useful out of this particular fine type of earthenware. Then another variety which is very much similar to that of your stone variety. So, in that stone variety what we get, the articles are impervious to water, because it is basically stone, it is stone like structure, stone like material and stone like property. So, it will basically repel the water. So, water will not go inside, that means it is not a porous material, it cannot have some water absorption capacity, and it is also only lightly glazed, because the other material can have higher glazed material and fractured and acid and alkali resistant. Since it is very much a stoneware type of material, because the stone utensils, stone like utensils also we know that how we make all this. So, the different companies are also making this for our day to day use or some special purpose uses also. So, the material, its corresponding property can also be improved by addition of barium oxide and zirconium dioxide also, that means BaO or ZrO2 like that of our other oxide material. So, what other oxide material along with your alumina or silica, because mostly these are material based on alumina and silica, but we can utilize some other variety of barium oxide or zirconium oxide to make the improved quality such that your acid and alkali resistance power can also be increased. Then the other well known property of that particular material, we know that how we make the porcelain. So, ceramic industry can also give rise to us the different types of porcelain material. So, these porcelain materials, that means the packing of these particles, the finer particles while firing, the corresponding packing of those materials are very dense. This is white in color and is also having a glassy surface. The surface nature is also very much improved. So, it is neither porous nor a stone like impervious in nature, but it is typically a glassy, and you can have a very thin walls and which is translucent and used in dental ceramics also. So, dental enamel can also may be made out of that. that we will also see, because the enamel industry is also another industry that will follow after we finish this particular part, that means the ceramic industry. So, the dental ceramics, the dental enamel also we can make out of this, but out of that if we can try to get first the ceramic, not the enamel. So, the dental ceramic can also be made. So, is the initial casting of the dental surface is done by the dental ceramic, then that uppermost crust can also be given by it out of that. Our fluorapatite type of material, which is your typical dental enamel. Then the different types of sanitary material also we can have, those are sanitary wares also we can have out of these porcelain, because that texture is completely different compared to that of the first variety. Then we go for the variety what we have started discussing our thing, that is the specialty ceramic products what we can have in our hand and how we quickly make these out of these reactions. Basically what we have, that oxide ceramics. So, our starting material is therefore your oxides. We have seen all these things out of that of your alumina as well as silica. What other oxides we can use for this particular purpose? So, it can have a single phase oxide material. So, single phase oxide metal ion oxides are the raw materials and should be very pure in nature, because the purity should be high. That is why the quality of that material, the cost of that material will also go up. That is why we are considering these as the specialty ceramic products. So, these specialty ceramic products can be made out of your typical check in the purity. So, the first of this category can be your oxide material. So, that oxide material out of your aluminum. So, aluminum oxide what we have seen. So, we are utilizing alumina as well as silica in the bulk material. So, this aluminum oxide typically can be used as the different raw materials. So, these raw materials what we can have is, one is the heated or calcined alumina Al2O3, not that you can have a particular variety which is cheap also, not that alpha, you can have the beta, you can have the gamma, because the gamma variety, if there is not a good source, you can have the cost of the gamma variety would be more than. So, a particular, so the raw alumina form only, so it can be a mixture of all the different varieties. Then the melted corundum, which is also the alumina Al2O3, then the sintered corundum. So, different types of corundum you can have. Then these are the raw materials, because this aluminum oxide material can give you a high temperature withstand. So, it can resist a very high temperature for a particular use. You can have the corresponding crucibles also, that aluminum oxide crucibles also. It can have good thermal conductivity, because it is not giving you a very bad thermal insulation, high electrical resistivity. So, it is basically a resistor in the electrical industry, and you can have also for the chemical resistance. So, the material we are making out of this aluminum oxide ceramic products. So, ceramic products can be utilized for handling different types of material, for the container for handling the different types of chemical substances, because it is very much resistance to not only acids and alkali, but the other type of chemical attack. For making the corresponding zirconium oxide based specialty ceramic products, we will use the zircon, which is zirconium silicate, and we can apply it for furnace construction. So, special type of furnace we can have, then resistive heating elements and neutron reflectors. In nuclear reactors, sometimes we can use we can reflect the neutrons, the neutron flow is there, the neutron as the particles which is flowing from one end to the other. So, if we use some amount of reflection out for those reflectors, we use as the corresponding zircon material is nothing but your corresponding zirconium oxide ceramic. So, the zirconium oxide ceramic can also be utilized. Then we can have the uranium oxide or thorium oxide based specialty ceramic material. So, that basically can give us using that uranium O2, that means UO2 pellets, and are manufactured using the dry pressing process. So, in that particular process, the dry pressing process is giving you the only another variety or specialty variety of that uranium based or the thorium based material. Then beryllium oxide. So, beryllium oxide can also give rise for the corresponding sintering process, which can be dry one, and which is plastically pressed into fine powders of beryllium oxide. So, beryllium oxide, which is BeO, at a very high temperature of 1400 to 1450 degrees centigrade, you get the corresponding material, the ceramic material, as the beryllium oxide material. Then others we can have the mixed material like magnesium doped aluminate, then yttrium oxide, or the beta variety of Al2O3. So, when we get these as for the corresponding use of electro and magnetoceramics, for getting these as the different types of electro and magnetoceramics, what we use? We can use the different types of titanates. So, these titanates are basically our corresponding process where we use the barium titanate. Sometimes these barium titanates are the typical raw materials from the nature we get it. So, if we get this from that particular one, that how we make the corresponding barium titanate material, we simply take titanium dioxide, which is your source of rutile. So, rutile is a fine white powder which is naturally available also, which is the most important titanium ore basically. So, that titanium ore as your rutile material. So, the rutile material, when it is burned in presence of your barium carbonate, we get the barium titanate, that means the barium salt of that titanate. So, these titanates are utilized for electro and magnetoceramic material, and carbon dioxide will be removed, and these are very useful material in electrical industry or the magneto-electrical industry also, because these are dielectrics for the different types of condensers. Because the small condenser we make, we know that for the ceiling fans also we use the condensers. These are oil based condensers, but if we use the solid state condensers, we can go for the different titanates for that particular one. Then cold conductors, then piezoelectric applications in microphones and other transducers. That means single transducing process can be done with the help of making this particular material, which is nothing but your barium titanate. So, you see that oxides you can have, the different types of oxides we can have. Now, the typical titanate. So, it is not a titanium dioxide based material, but it is a titanate one, because titanium dioxide can have two oxygen centers attached to the titanium. If you put more titanium, so you can have a different structure in it. If you are putting more oxygen centers around the titanium, and these are like your ferrites and other material, is basically the titanates for different types of applications. Okay, thank you very much.